Hello students, I am Dr. NAVNEET KAUR, Associate Professor in Department of Electronics and Communication Engineering, SIRT College, Bhopal. Today I will be taking lecture on subject Digital Signal Processing. The topic of the lecture is Discrete Time Systems. This is my fourth lecture of Digital Signal Processing. In my previous lecture, I had discussed about types of discrete time signals and operations performed on these signals. In this lecture, I'll be taking discrete time systems in detail and the properties of these discrete time systems. Now, what is discrete time system? A discrete time system is a device or an algorithm that takes a discrete time signal as an input and generates a discrete time signal as output. The most common example of discrete time system is a digital filter. For example, we have a low pass filter. Whenever a noisy signal is given to a low pass filter, the low pass filter removes the effect of the noise and generates a clean signal. So here the processing is done on the noisy signal and a new output signal is generated. So low pass filter is considered as a discrete time system because here we are giving discrete time signal as an input and generating a discrete time signal as an output. Mathematically, the notation of any discrete time system is given by y is equal to t of x, where x is the input signal, which is also known as excitation, y is the output signal, which is also known as response, and t is the operation of the discrete time system. So whenever this operation is performed on the input signal, output is generated. So it is written as y is equal to t of x. Now, coming to the different properties of the discrete time system, or we can say the classification of the discrete time system. Now, the first type of the discrete time system is static and dynamic system. The static system is the system in which the output yn at every value of n depends only on the present input at the same value of n. It does not depend on the future inputs or past inputs. The common example is yn is equal to xn whole square. Here yn is the output, xn is the input. So here present output depends only on the present input. It does not depend on the past or future inputs. And the system which does not obey this rule, that means it depends also on the past and future inputs, is known as dynamic system. Now next is linear and non-linear system. Linear system is the system which obeys or which follows superposition principle. That means it should obey additivity property and homogeneity or scaling property. Additivity property means, suppose I have any system whose operating function is t. Say input x1n is given and output y1n is generated. x2n gives y2n as output. Now, if I add these two inputs, x1n and x2n, and gives to this same discrete time system, I should get the output as the sum of these two outputs, y1n and y2n. This is additivity property. Similarly, I have homogeneity or scaling property. Homogeneity property is that if I multiply an input with any scaling factor a, then I should get the output multiplied by the same scaling factor. That means if xn generates yn, then axn should generate ayn. So these are the two properties which combines to form the principle of superposition. Now, if any discrete time system follows this principle of superposition, that means the system is a linear system. That means if x1 and x2n, they are multiplied by scaling factors a and b respectively and are added and are given to the system. In that case, the output will also be y1 and y2n multiplied by a and b and are added together. That means a operating function when acts on x1n plus b operating function when acts on x2n. That means two outputs multiplied by same scaling factors are added together. This should be the output. So this is known as principle of superposition. If any system obeys this principle of superposition, that system is known as linear system. Now, common example of the linear system is an accumulator system. Accumulator system means that at any instant n, output should depends on the sum of the inputs from previous instance, that is from minus infinity to the present instant, that is n. That means it should be written as x of minus infinity plus x of minus infinity minus 1 and so on. That means it will be x of minus 2 plus x of minus 1 plus x of 0 plus x of 1 and till x of n. Now, I'll have to prove it that whether an accumulator system is a linear system or not. Now, say if I have two inputs x1n and x2n and it generates output y1n and y2n. y1n is given as k is equal to minus infinity to n x1k. y2n is given as k is equal to minus infinity to n x2k. When I have another input which is given as ax1n plus bx2n, in that case, the output will be summation x3k, where k is again from minus infinity to n. x3k is ax1k plus bx2k. Now I'll separate the two summations. Since a and b are constant, they can be taken out of the summation. So a summation x1k plus b summation x2k, and we know that this part of the summation is y1n and this part of the summation is y2n. That means it is equal to ay1n plus by2n, which is the principle of superposition. So accumulator system satisfies the superposition principle. Therefore, it is an example of linear system. Now, we have one more example, which is a squarer circuit. Squarer circuit means if any input is given to a discrete time system, then the output should be the square of that particular input. Now, in that case, it will be a non-linear system, because if we have two inputs, say 1 and 1, and we will square these two and add, then it will not be equal to if these two inputs are added and squared. So this is a non-linear system. Now, next is classification is time invariant system. Now, time invariant system is the system whose characteristics does not varies with time. That means if say I have any discrete time system and I give input x1n and output y1n is generated. Now, if I delay the input by say instant n naught, and I'll give this delayed input to the same system, in that case, there should be no change in the shape of the signal. Only the output should be delayed by the same instant by which the input was delayed. That means the output should be again same y1, but it should be delayed n minus n naught. It means that the characteristics of the system does not varies with time. Only if the input is delayed, then output will also be delayed. In that case, the system is known as time invariant system. And the system which does not follow this rule is known as time variant system. Now, example of the time invariant system is, say, I check accumulator system. Accumulator system, which I have already discussed, is given as yn, which is output. It is equal to summation k is equal to minus infinity to n xk. Now say my input is delayed by n naught, that is xn minus n naught. Now in that case, y1n will be summation k is equal to minus infinity to n x1k, where x1k will be written as xk minus n naught, which is from minus infinity. Say I'll substitute k minus n naught as, say, n. In that case, k minus n naught as, say, k1. In that case, since my variable is changed, the limits of this variable will also be changed. So k1 new limits will be minus infinity to n minus n naught x k1, which is y n minus n naught. That means I'll get the same output, but it is delayed by the same amount by which this input was delayed. So this system is a time invariant system. Now consider, say, compressor system. Compressor system will time scale any signal by factor, say, capital M. Now, if input is xn, then yn will be x capital M n, where m, capital M, is the scaling factor. Now, say I'll say capital M, I'll take as 2. So if, say, I'm giving xn, then I should get x2n. Now say input is delta n, I'll give it to the system and I'll get delta 2n. Now if I delay the input by, say, unit 1, so I'll get delta n minus 1, which I'll give to the system, and I'll get delta 2n minus 1, which is delayed by same amount 1. That means in this case, the output which is delayed by the amount by which input was delayed is not equal to the delayed output. So the system is time variant system. It is not a time invariant system, because here the characteristics of the system is varying with time. Now, next property is causality property. A system is causal if for every value of n naught, the output sequence at n is equal to n naught depends only on the input sequence value for n less than equal to n naught. That means a particular output at particular instant depends only on present and past sequence. It does not depend on the future inputs. Now, considering an example for causal system. Forward difference system, we'll see that it is not causal system. Forward difference system is represented by this equation, yn is equal to xn plus 1 minus x1. Now say if I take n as 0, so it will be y0 is equal to x1 minus x0. That means y at instant 0 depends at x at instant 1. That means present output is depending on the future input. So the system is not causal. Whereas backward difference system is a causal system. Backward difference system is given by this equation, yn is equal to xn minus 1. Now say if I take n is equal to 0. Now it will be written as y0 is equal to x0 minus x of minus 1. That means y at 1 depends on x at 1 and x of minus 1. That means it depends only on present input and past input. It does not depend on future input. Now if I'll take every value of n, I should get that the system, the output of the system depends only on the present and the past inputs. Therefore, the system is a causal system. Now, the next property is the stability property. Now, a signal is a bounded input or bounded output signal if it has a finite amplitude at every instant of n. Now, Here we will consider the Bibo stability property. That means if my input sequence is a bounded sequence, then it should produce a sequence which should also be a bounded. Therefore, it is known as bounded input, bounded output stability, or we call it Bibo stability. That means if my input is less than equal to say some value Bx, which is less than infinity, that means Bx is a finite value for all n, then Yn should also be a finite value, say By for all n. Then only the given system will be a Bibo stable system. Now, we will check the stability of the system which is given as Yn is equal to Xn square. Now say if input Xn is a Bibo stable. Now, in this case, if it is a bounded signal, Xn is say bounded signal, then whenever we'll square the finite value, bounded signal means that it is having a finite value for all values of n. Now, whenever I'll square the finite value, I'll again get a finite value. That means Yn will also generate a finite value By, which should be less than infinity for all n. So in that case, if Xn is bounded, Yn is also bounded. Therefore, the system is stable. Now, consider another example, say accumulator system, which is Yn, where k is equal to minus infinity to n xk. Now, this is again a stable system because here the value of the, well, this is an unstable system because here as we add xk for k is equal to minus infinity to n, since k is going from minus infinity to n, it will have to add up infinite values. So in that case, the output will not be a bounded. So this system will be an unstable system. Now consider if I'll say Xn is equal to say Un, which is unit step input. Now unit step input, we know it is 1 when n is greater than equal to 0 and it is 0 when n is less than 0. Now if I'll consider an accumulator system Yn, which is summation k is equal to minus infinity to n of xk, then we'll get, say the value of the input Xn is 1. Now, if n is less than 0, the value will be 0. But if n is greater than 0, the value will be n plus 1 because from k is equal to 0 to n, there are n plus 1 values. So it will be n plus 1. Now, if n is going to infinity, naturally the value of Yn will also tends to infinity. So the output will not be bounded and the system will be unstable system. So accumulator system is not stable. Now, what is linear time invariant system? Now, in my previous slides, I have discussed about the linear system and time invariant system. Now, system is if linear as well as time invariant. In that case, the system is known as linear time invariant system, which is LTI system. Now, suppose if the system is LTI system. Now, if I'll give input delta n, the output we know is Hn, which is known as unit impulse response. Now, if I'll delay delta n by unit n naught, then because the system is time invariant, the output will also be delayed by same amount n naught. So delta n minus naught should give Hn minus n naught. Now, we will consider the representation of the general sequence as a linear combination of the delayed impulses. Now, if I have any sequence Xn, it can be represented as the sum of the weighted and shifted impulses. That means it can be written as x0 delta n plus x1 delta n minus 1 plus x2 delta n minus 2. Say if I'll take negative values of k, then x minus 1 delta n plus 1, x minus 2 delta n plus 2, and so on. So this is the representation of any general sequence in terms of the delayed impulses. Now, according to the principle of the superposition, now if I want to generate output for this particular input yn, then it will be the system operator which is acting on the input xn. So I have written summation xk delta n minus k in place of xn. Now, since it is a linear system, so it will be summation xk. T will act on delta n minus k because delta n minus k is dependent on n. Now, we already know that if the system is time invariant, then delta n minus k, if it is the input, then it should generate an output h minus k. So this will be the formula for the convolution, which is according to the rule which generates the output yn. So yn is given as linear convolution of xn and hn, which is given by the formula summation k is equal to minus infinity to infinity xk h minus n minus k. Now, this linear convolution is always commutative. That means if xn is convoluted with hn, it will give the same result if hn is convoluted with xn. That means if xn is given to hn, then it generates output yn. Then it will be same as if hn is given to the system with unit impulse response xn, and it will give the same output yn. Now, convolution is also distributed over addition. That means xn in convolution with h1n plus h2n will be equal to xn in convolution with h1n plus xn in convolution with h2n. Now say, if I have an input xn and I'll give it to two systems with unit impulse response, say h1n and h2n, which is given here. So xn is given to h1n and h2n, and the output generated is added, it will give yn. Then according to the distributive principle, it should be as same input convoluted with another system which is having a unit impulse response h1n plus h2n. That means this equation is written as xn is given to the system with unit impulse response h1n plus h2n, and output yn is generated. That means this parallel combination of two discrete time system can be represented by one discrete time system whose impulse response is the sum of these respective impulse responses. Now again, if I consider cascade connection of the system, say if xn is given to one system h1n and the output is given to the second system with unit impulse response h2n, then we will get the final output yn. Now, if these two systems are in cascade, that in that case, we can represent it with a single discrete time system whose unit impulse response is the convolution of the respected unit impulse responses h1n and h2n. That means what we have concluded, that if two discrete time systems are in parallel, in that case, we will get a resultant system whose impulse response is the sum of the respective unit impulse responses. And if two discrete time systems are in cascade, then we will get a resultant discrete time system whose impulse response is the convolution of the respective unit impulse responses. Now, we will express the stability of the LTI system in terms of the impulse response. Now, LTI system is stable if its impulse response is absolutely summable. That means impulse response is hk if its summation of k is equal to minus infinity to infinity is also less than infinity, then we will say that the given LTI system is a stable system. Now we know yn is given as summation k is equal to minus infinity to infinity hk xn minus k. Why have written h as first and then x? Because we know convolution is commutative. I can write it as xk hn minus k, or I can write it as hk xn minus k. Now I'll separate these two absolute value, which will be less than equal to, using this inequality, hk xn minus k. Now, suppose the input signal is bounded. That means xn is less than equal to, say, some finite value bx. Then yn, absolute value of yn, will be less than equal to bx, because the value of xn minus k is also bounded bx, and summation hk, absolute value, less than infinity. Now, we know bx is a finite value. If yn has to be finite, then this summation should be a finite. That means summation k is equal to minus infinity to infinity, hk's absolute value should be less than infinity. So this is the condition for any discrete time system to be stable. Now this is all for today's lecture. Thank you.